Most AI deployments do not become efficient when they scale. They become more expensive. They fail because scale was misunderstood. And once that mistake is made, costs do not go down, they compound. Economies of scale in model deployment do not begin with intelligence, they begin with cost behavior. At small scale, AI looks expensive, unstable, and operationally heavy. Every request feels like a decision. Every output carries marginal cost. Every deployment looks like an investment that still needs to justify itself. But that perception is temporary, because once deployment crosses a certain threshold, the economics invert. The same system that felt expensive begins to distribute its cost across volume. The same infrastructure that looked oversized becomes fully utilized. And the same model that required justification starts behaving like a baseline utility. This is the moment where AI stops being a tool and starts becoming an economic structure. The core mechanism is simple. Model deployment carries a large fixed cost layer: training, integration, infrastructure, orchestration, monitoring. These are not costs that scale linearly with usage. They are front-loaded. They exist before value is realized. But inference, the act of using the model, behaves differently. Once deployed, each additional use carries a relatively small incremental cost compared to the initial investment. Not zero, but compressed. And that compression is where scale begins to matter. At low volume, fixed costs dominate. The system feels inefficient. Cost per unit is high. ROI looks uncertain. At high volume, fixed costs dissolve into the background. Cost per unit declines. The system begins to produce economic leverage. This is not about cheaper AI. This is about spreading cost across time, volume, and surface area. The more the system is used, the more economically efficient it becomes. This shows up directly in the cost structure. Lower unit cost, higher total spend. But this only holds under one condition: utilization. A model used at 10% capacity is expensive. The same model at 80% becomes economically efficient. If deployment scale increases without utilization, the economics break. Infrastructure sits idle. Models are underused. Capacity becomes a burden instead of an advantage. Scale without utilization is not efficiency. It is stranded capital. This is where many organizations misread AI economics. They assume that deploying more models creates advantage, that expanding capability leads to efficiency, that having more AI means lower costs. But scale is not about quantity. It is about density of use. A single model used across hundreds of workflows produces more economic efficiency than dozens of models used sporadically. Because economies of scale in AI are not driven by model count. They are driven by deployment saturation. How many times the same system is used, how broadly it is integrated, how deeply it is embedded into operations. This creates a second-order effect. As utilization increases, not only does cost per unit decrease, but operational behavior changes. Decisions become faster because the system is already in place. Workflows adapt around the model instead of resisting it. The organization stops treating AI as an external tool and starts treating it as internal infrastructure. An infrastructure behaves differently from tools. It is not evaluated per use. It is assumed. Electricity is not justified per device. It is embedded. Cloud computing is not evaluated per process. It is integrated. At sufficient scale, AI begins to follow the same pattern, but an additional cost layer emerges at scale. As deployment expands, coordination, monitoring, reliability systems, and redundancy requirements increase. Operational overhead grows alongside usage. Efficiency does not decline, but it plateaus. Each expansion in scale introduces a new layer of management cost. This is not a failure of the model. It is a property of operating large systems. There is also a temporal constraint. Models do not evolve continuously with their environment. As conditions change, performance can degrade relative to the context in which the model operates. The more deeply a system is embedded, the more expensive it becomes to update, replace, or retrain without disruption. Scale increases efficiency, but it also reduces flexibility. This creates a fundamental tension. Efficiency improves at the unit level, but aggregate spend grows with usage, which means scale can simultaneously improve margins and increase total cost exposure. This is the paradox of AI deployment. More usage makes the system more efficient, but more usage also increases dependency, and dependency introduces risk. Because once an organization restructures around scaled deployment, it becomes difficult to reduce usage without disrupting operations. This is economic lock-in, not through contracts, but through behavior. Workflows adapt. Teams rely on the outputs. Processes assume availability, and the system becomes embedded. At that point, reducing scale is no longer a financial decision. It becomes an operational disruption. This is where economies of scale transition into economies of dependency, and that transition is rarely visible at the beginning. Early deployment feels optional. Late-stage deployment becomes structural. Now consider competition. When one firm reaches genuine scale, its cost per unit drops meaningfully. That allows it to operate at lower prices, higher margins, or both. Competitors without similar scale face a different cost structure: higher per unit costs, lower operational efficiency, reduced pricing flexibility. This creates pressure, not because the model is better, but because the economics are. And once multiple firms reach scale, another shift occurs. The cost advantage compresses across the market. Efficiency becomes normalized, and pricing pressure increases. This is where scale stops being a differentiator and becomes a requirement. At that point, the question is no longer, should we deploy AI? It becomes, can we operate without it? Because once economies of scale establish a new cost baseline, not participating is equivalent to operating with a structural disadvantage. Higher costs, slower processes, reduced flexibility, and over time, reduced competitiveness. But there is a final layer. Not all scale is equal. There is a difference between scaling compute and scaling value. Compute scale reduces unit cost, but value scale determines whether that reduction translates into real advantage. If increased usage does not improve output quality, decision quality, or revenue generation, then scale only improves efficiency, not performance. And efficiency without performance is not sustainable advantage. It is operational optimization, which competitors can replicate. So the real economic question is not whether scale reduces cost. It does. The question is whether scale compounds value, because only when scale improves both cost structure and output quality does it create durable advantage. Otherwise, it accelerates commoditization, and this is the end point of model deployment economics. At small scale, AI is expensive and uncertain. At medium scale, it becomes efficient and leveraged. At large scale, it becomes expected. And once it becomes expected, the advantage disappears. What remains is the structure. Lower marginal cost, higher dependency, tighter competition, and a system that is no longer optional, but foundational.